Okay, so 7.4 is the last section before we actually start solving differential equations. So this is the last piece we need. It's transforms of derivatives, integrals, and periodic functions. And I forgot a C. Not funtions, but functions. Sorry. Okay, so the thing that we're most concerned with right now is the transforms of derivatives. So we want to look at stuff like the Laplace transform of dy dt, the transform of the second derivative, and maybe from that we can kind of gather if there's any pattern or some general rule that we can apply no matter what the order of the derivative is. Okay, so to do that, we'll apply the definition. So if we just want the Laplace transform of a derivative, let's just call it f prime of t. That would be the integral from 0 to infinity of e to the minus st f prime of t dt. And even though we don't know what f of t is, since it's the derivative, when you do the antiderivative, the integral is easy. It's e to the minus st f of t, and that's evaluated from 0 to infinity, or at least take the limit as t goes to infinity. Nope, I'm missing something. We should be doing integration by parts here, because we do have 2t, so it's not quite as easy as I thought. This part will be there. We can call this u and this v, or dv. There we go. So then when you integrate, you get uv. So here's our u and v minus the integral of v du. So that would be the integral of f of t, 0 to infinity, and then du would be s, will be negative s. So let's make this a plus. So plus s e to the minus st dt. Okay? So now let's see what happens. As t goes to infinity, this will go to 0. When you plug in 0, you get minus f of 0. Plus, let's see, you could factor out the s, since it's not the variable we're interested in here, so we'll leave it as s times the integral from 0 to infinity. And let me just rearrange things so that maybe it's a little more obvious. This is what? Transform. So, if we want the transform of the derivative, we can just take s times, let's call it capital F of s, since this is the definition of a transform. And we still have our minus f of 0. Okay? So the Laplace transform of the derivative is s times f of s minus f of 0. Now, we don't have to do very much more than this, but here's what it's going to look like. If I want the Laplace transform of f double prime of t, you can think of a substitution. Consider this the first derivative, follow the same pattern here, right? Except everything is 1 prime higher. So we would have minus f prime of 0 plus s, and then we have the Laplace transform of f prime of t, as opposed to the Laplace transform of just f prime. I'm sorry, of just f. And now here, what we'll do is apply the pattern that we've seen one more time. So let me put that term first. We'll have s, and then the transform of f prime, I'm just plugging in s times f of s minus f of 0. And we still have minus f prime of 0 from above. So we get s squared times the transform minus s times f of 0 minus f prime of 0. Okay, and you might be able to see the pattern here. First order derivative starts with just s times the transform. Second order derivative starts with s squared times the transform. And then you basically decrease the s's by 1 each time as you work your way up from 0 derivative, first derivative, all the way up to as many as we need. So here's the general rule or theorem. If f of t, f prime of t, and so on, all the way up to the nth derivative, are continuous and of exponential order, and if the nth derivative is at least piecewise continuous, on 0 to infinity, then the transform of an nth order derivative starts with s to the n times the transform of s, or of t, which is capital F of s, minus, and now we just start to decrease the exponent of n. So it's s to the n minus 1. So here the exponents for s decrease. And then now here you start with f of 0 and you work your way up. So the next term would be s to the n minus 2. So again, these just keep decreasing. And now this becomes f prime of 0. And we keep working our way up. Until we get to the term without any s, and then that would be the n minus first derivative evaluated at 0. And of course it's understood that capital F of s is indeed the transform of f of t. But rather than write that notation out over and over, capital F of s makes more sense. Okay. Any questions on this so far? Okay. Let's talk about the convolution theorem. Which says the following: if f and g are piecewise continuous, on 0 to infinity, then the convolution of f and g is, and we use a little asterisk. That's the symbol for convolution. So this means f is being convoluted with g, and the definition is to take the integral from 0 to t of f of tau, g of t minus tau, d tau. The convolution of two functions commutes, so f convoluted with g is the same as g convoluted with f. You'll get the same result. I should probably clarify. This isn't the theorem yet. This is just we're building up to the convolution theorem. This is just the definition of convolution. So maybe we'll scratch this out. We'll build up to the theorem. Let's try an example with this one. This part, to apply it, isn't very hard. I think you guys will get the idea when you see the homework problem. You just plug in the condition f of 0, and it's pretty easy to work with. This can be a little bit tricky. So let's go ahead and look at, let's say we want to have e to the t, and we're doing the convolution of that with sine of t. Okay, so this would just be the integral from 0 to t of what? What two functions do we see? We have exponential and sine, right? So pick one. Let's say this is f. So this would be e to the tau. Yep. Okay, and then this looks kind of like those transforms from before when you had the exponential with sine. So you're going to have to do integration by parts. So let's do u equals e to the tau. Du would just be e to the tau again. And dv would be sine of t minus tau. So then v, if we integrate, would just be cosine of t minus tau. Alright, so let's plug it in. uv would just be e to the tau cosine of t minus tau evaluated from 0 to t minus the integral from 0 to t of v du, I'm sorry, u dv. No, v du is fine. So cosine t minus tau du is e to the tau d tau evaluated from 0 to t. Plug in 0. What do you get? Or plug in t first, sorry. We got e to the t. T minus t is 0. Cosine of 0 is 1. Now we plug in 0. E to the 0 is 1, so then we have cosine of t. That should be e to the t, sorry. Thank you. Okay. So now we still have this guy to worry about, so I'm going to subtract, and then this gets treated pretty much the same way we treated the integral that we started with. So that would be, let's see, I'll do the same thing. U is going to be e to the tau, so then du is e to the tau d tau. dv will be cosine of t minus tau, so then v will be negative sine t minus tau. Okay, so if you plug all these guys in, we have uv, so negative e to the tau sine of t minus tau, evaluated from 0 to t. And we're going to subtract the integral of v du, so we're going to add the integral from 0 to t of e to the tau sine of t minus tau d tau. Okay. So if we clean some things up, if you plug in t gives us sine of 0, so that's 0 entirely. And then we're going to have plugging in 0, so sine t, adding, but we're subtracting here, so minus sine t. And now we're subtracting this, which is actually the same as e to the t convoluted with sine t. So this portion here, that's the same thing we started with. So we can do the same technique we did whenever you do integration by parts twice. You factor out what it is that you're solving for. So here's what we have. We have 2e to the t after you move this over. So if I set this equal to this, you add this to the left, you get 2e to the t convoluted with sine t, and then that equals e to the t minus cosine t minus sine t. And then just divide by 2, and there's your convolution of e to the t and sine t. Not every single convolution of two functions is this involved, but this is one of the trickier ones. Okay. So now here is the convolution theorem. Okay, yeah. So hopefully you're wondering, well, what is the point of this silly convolution? Seems kind of like it's coming out of nowhere. Well, here's the benefit of it. Let's say we have f of t and g of t. And of course we have that they're piecewise continuous. On 0 to infinity, and of exponential order. Then, the Laplace transform of a convolution of f and g is simply equal to the Laplace transform of the product of f times the Laplace transform of g, which is the same as capital F of s times capital G of s. We're going to omit the proof just because we're getting short on time. I want to make sure we finish, but here's what you need to remember. This and the inverse form, which we'll talk about in a minute, will be pretty useful. Here's an example going one direction. So let's say we have the Laplace transform of the integral from 0 to t of e to the tau sine of t minus tau d tau. Okay, so we did the hard part already, but now that we have the convolution theorem, if you recognize what two functions it is that are being convoluted, you don't have to do all that integration by parts a couple of times and then do it the long way. If you recognize what two functions they are, then you can just take the Laplace transform of each of those two functions. Okay? So of course one option would be to do the definition and then do the transform of each one of these guys and then go there. Or if you recognize that you're convoluting e to the t with sine of t, then this is the same as the Laplace transform of e to the t times the Laplace transform of sine of t. And we know what the transform for each of these are. Laplace transform for e to the t is what? And transform for sine of t is 1 over s squared plus so 1. So, I mean, we can't really do much else. Let's just maybe combine it into one fraction and we're done. Okay, this is the same answer we would arrive at if we took this and manipulated it enough. Okay, but that would require more time and effort. Okay, so this is just going straightforward with the convolution theorem. One direction. I think the most useful of it is actually the inverse form. So let me show you that real quick. And that's if you are taking the inverse transform of two functions f of s times capital G of s. The key is recognition, though. If you don't recognize that you're multiplying two transforms, then this is kind of useless. If you recognize that you have two functions that happen to be transforms, then this is actually a pretty nice thing. This would be equal to what? If we're going the other way, this is the convolution of f and g. Okay? So here's an example to illustrate why you might be interested in this. Well, maybe you won't be. Who knows? Let's say you have the inverse transform of 1 over s minus 1 times s plus 4. One option that we have currently is to do what? Partial fractions, do the decomposition, which wouldn't be too bad for this because it's just an easy linear decomposition, and then you can find the transform of each of those. However, if you recognize that this is the same as the inverse transform of 1 over s minus 1 times 1 over s plus 4, then you can do the convolution, the inverse form of the convolution theorem. Okay? So here's what we have to do. What function gives us 1 over s minus 1? E to the t, right? And what function gives us 1 over s plus 4? E to the negative 4t. So as long as you recognize that these are the parent functions, so to speak, that produce these transforms, then instead of doing partial fraction decomposition, what you could do is convolute e to the t with e to the minus 4t and be done with it. Okay, so how do we do that? Well, we take the integral from 0 to t. I'll just go with f as my first function and g as my second one. So e to the tau times e to the negative 4, and then we replace t with t minus tau, d tau. We can combine the exponential terms. We'd have e to the 5 tau, and then e to the negative 4t d tau. Since we're integrating with respect to tau only, this is just 1/5 e to the 5 tau e to the negative 4t evaluated from 0 to t. So when you plug in tau equal to t and tau equal to 0, let's see, we get 1/5 e to the 5t times e to the negative 4t minus 1/5 e to the 0 e to the negative 4t. And now we just clean up our answer. 1/5 e to the t minus 1/5 e to the negative 4t. So I mean, it's not, I don't know if this is necessarily any faster than partial fractions for something as basic as the inverse transform of these two functions. Probably about the same, but it's just another option. Maybe there's another partial fraction decomposition that would just be a lot of work. If you check the convolution theorem, maybe you'll recognize that doing that is actually a lot faster. So, okay. I'm not going to have time to do the example, but I'll write down the theorem because you will use it a little bit in the homework. The transform of a periodic function so if we have a periodic function, let's say f of t looks something like this. This is the general picture here. What would the period be for this? Okay, so if you have a function that's periodic and the period is capital T, we're assuming it's piecewise continuous and all that good stuff. The inverse transform of this periodic function would be 1 over 1 minus e to the negative s times capital T times the integral evaluated from 0 to capital T of e to the minus st f of t dt. Okay, and what's going to happen well, you'll see, but what you'll be able to do is split this integral up into pieces, however many pieces there are for the period to repeat. In this case, this general function here, we just have the 1, so it'll be easy because you'll know what function this is and you can plug it in there and it won't be that difficult. But there are some functions that have 2 separate pieces before it recycles and starts repeating, right? So if that's the case, so this is as good as I can do today. Like if we had something like this, so we have line and then horizontal, line and then horizontal. You see how the period would be here, whatever that is? Does that make sense? What you can do is split the integral here up into these 2 pieces. So if the period is t, then you'll have some constant here. You can do the integral from 0 to c, figure out what that is, plug it in, and then from c to t. Does that make sense? Split it up into 2 pieces. Okay? All right. Tomorrow we'll go over homework. If you have any questions, which you might, we'll have time for them. Wednesday, we will finish the unit. Thursday will be a review. Monday exam. So I'll see you guys tomorrow.